Vertical kinematics. So these are objects that are freely falling. Freely falling. These things are objects that are just falling through the air. It is still considered constant acceleration to be an object that is in free fall. Now, answer this question. If an object is being thrown into the air, is that a freely falling object?
No.
It is. It is. Any object that's unattached, whether it's moving upward or downward, is a freely falling object, right? It might be moving in the upward direction, but gravity is still the acceleration that is responsible for that object's motion. So it is a freely falling object. So any object that's unattached is freely falling. Okay, it is a free falling object. Yeah.
So if you like take a rock and you chuck it straight up and it lands on top of the building, that's free falling. You know, like never starts as a coin.
Because what's it doing on the way up?
Slowing down.
It's slowing down. Yep. Yep. So acceleration is still acting on it. Answer this question without looking at the answer. Do heavier objects fall faster than lighter objects? I know, you already saw it. All right, do heavier objects fall faster than lighter objects? The inclination would be to say yes, right? I feel like that's a natural inclination to say yes. And people believed that for a very long time because Aristotle said it. Okay, and everyone at that point was able to believe what Aristotle said to be true, right? A lot of what he said was true. And so he said heavier objects fall faster than lighter objects. Then Galileo comes along and says, whoa, I don't think so. So then he went through this big theatrical experiment about whether heavier objects fall faster than lighter objects. And he went up to the Leaning Tower of Pisa, you know what I'm talking about? Right? Dropped two things off the building and, all the witnesses saw them hit the ground at the same time. And so this big dramatic showdown to prove his point. But what has to be true for objects to fall at the same rate is that they have to be relatively the same shape. They have to experience air resistance in the same way. So if I drop a sheet of paper versus a crumpled sheet of paper, these objects have the same mass, don't they? Right? This has the same mass as this. But which one's going to hit the ground first? This, right? Because it has much less opportunity to experience air resistance. But as this falls to the ground, the force that is pushing upward on it from the air, right, will make it reach what we call terminal velocity a lot quicker. And so then it will just kind of float down to the ground. Okay, so in order for objects to hit the ground at the same time, their mass really has nothing to do with it. It has to do with how they experience air resistance. I want you to take a look at your kinematics equations. Take a look at your kinematics equations for me. Pull those out. Do we put mass into the kinematics equations anywhere? Do we put mass into the equation? We don't, right? So that's another indicator for us that mass has no correlation with an object's velocity displacement, right? As long as we're living in our perfect physics world, which in high school physics we get to, right? We're in a perfect physics world, that's not affecting those things. In reality, mass has an effect on an object's friction, right? How much friction it is experiencing. Mass has an effect on all sorts of different things. But in our perfect physics world, when we're studying motion, we can assume that mass has no effect on our object, right? As long as they have the similar shape. So, okay. Let's talk about objects that are moving vertically. This is what we're talking about today. Objects that are moving vertically experience the acceleration due to gravity. Acceleration due to gravity. And that means every vertical problem you do will have an acceleration of negative 9.8 meters per second squared. Every vertical problem you do will have an acceleration of negative 9.8 meters per second squared. Let's see. Tell me, why is my acceleration negative? Okay. Kind of, yes, right? It's pointing in the downward direction, but does acceleration always negative if it's going downward? No, so let's talk through a couple scenarios here. If my object is launched into the air, it's moving in the positive direction, isn't it? And what is it doing as it's going in the air? Is it speeding up or slowing down? Slowing down, which would mean my acceleration is negative. Agreed? Right, that's a scenario in which I have negative acceleration. Let's say that an object starts at the top and is dropped. This has negative direction, doesn't it? And what is it doing? Speeding up or slowing down? It's speeding up. And so this would also have negative acceleration. Right? So the acceleration due to gravity is always negative 9.8. I need you to hear me say that, because regardless of if my object is moving upward or downward, A is still negative 9.8. Okay? All right. We said our acceleration due to gravity is negative 9.8. Sometimes, instead of writing A, we give that variable with a lowercase g for gravity. Okay? I am going to give you the option as to whether you want to rewrite your equations with vertical variables, or if you just want to be able to use the kinematics equations you have and apply them vertically. It's really up to you. But if I was going to rewrite them vertically, I might say Vyi equals Vyf, plus gt, right? That's my first one, right? What does this represent? Vyi. What do those subscripts tell me? It's velocity, and then what is it? What does the y-axis represent? Horizontal motion or vertical motion? Vertical motion. So when we see y, it means we're talking about the vertical velocity, right, my object. You don't have to put that in there. If you want to, you can. And then, so Vyf would mean vertical velocity final, right? Velocity in the vertical direction final. So those subscripts all mean something. They contribute to what that variable is representing, okay? My next equation would look like this. Y final equals y initial plus Vyi times t plus 1/2 gt squared, right? And so y final is displacement. It's measured in meters. It's like the height of my system, right? How far my object is falling or how far it's going. It's just vertical displacement. Okay, we use x for horizontal because that's the horizontal axis, and we use y to represent vertical because it's the vertical axis. So our last equation would be Vyi squared equals Vyf squared equals Vyi squared plus 2g delta y. Okay, you don't have to rewrite those. I probably wouldn't rewrite them on your equation sheet because I think it'll make it a little cluttered, but you are welcome to. I think once we get familiar enough, you'll be able to apply the equations you have in the vertical direction. Okay? Let's talk about a couple other things here as we talk about freely falling objects. Tell me, if my object is launched through the air, we already said it's slowing down on its way up. Do we agree with that? What's the velocity of my object at the highest point? It's 0, right? For just that split second, it pauses and then it falls to the ground again. So I will oftentimes call this an object's peak height. Okay, does that phrase make sense to you? Peak height just means the highest point that it's going to reach. Okay, so an object's peak height, its velocity is 0. Okay, its velocity at its peak height is 0. Okay. Tell me what questions we have so far. Okay, what would, as my object falls to the ground again, the direction of the velocity, what would it be? Would it be positive or negative? It would be negative velocity. We would have negative velocity as it falls because now it's moving in the downward direction. Our velocity would be negative. We're going to have to do a couple math things there to make that work in our equations, but I'll walk you through that as we get through it. Okay? Just go ahead and try one here. It says, suppose that a ball is dropped from a tower 70 meters high. How far will it have fallen after 1 second, 2 seconds, and 3 seconds? So I'm going to come over and draw my little diagram over here. Okay, it tells me that tower is 70 meters. Okay, a ball is going to be dropped. And it's asking me What's the overall point of my question here? How far will it have fallen? What's my final... I'm looking for displacement, aren't I? That's going to be my final thing, is that my YF is my question mark. That's what I'm solving for. Now, answer this. Can I solve this in one equation? Can I solve for 1 second, 2 seconds, and 3 seconds in one equation? I can't. I'm going to have 3 different answers here, so it will take me doing this problem basically 3 times. Okay, let's talk about a couple things here. We know that in our first problem, our time will be 1 second. There's another piece of information from the problem that is a context clue for us that we need to be familiar with. When it says that my object is dropped, that means, any idea what that means? It has to do with my initial velocity. It's at 0. My initial velocity is 0 because the second it leaves my hand and becomes a freely falling object, it's not in motion until acceleration starts pulling it downward, right? The exception to that would be if I throw an object, right? That means it would have an initial velocity. But anytime we see the word dropped, it should tell us that my initial velocity is 0, okay? So that means VI is equal to 0. All right, one last piece of information for us to think about when we start our problem. We've mentioned a couple times how I like to put the origin at the beginning of my motion. Do you remember we're talking about that? I like to do that so that my initial displacement can be equal to 0. Okay, if I didn't do that, I would make my initial displacement 70. And so then it just comes a little bit sticky as to what my final answer will come out. I just much prefer to have my initial be 0, and then my final displacement will tell me how far I am from my starting point, right? And I might have to do a subtraction after that, but I might not, okay? And it will tell me that. Let's ask the question here. Will my displacement, do you expect my displacement here to come out as a positive answer or a negative answer? Right? My ball is falling downward. Do you think my answer will come out as a positive displacement or a negative displacement? It should come out negative. That will tell me my ball is going to end up below where I started. That's what a negative displacement here tells me, that my object is falling below where I started. Okay, so I gave us lots of preliminary stuff here, but let's see, do we have an equation that would let us solve for this? We don't have a lot of information, do we? What's one thing that we always know about the acceleration in vertical problems? What is it? Negative 9.8. Now, do you have a preference as to whether we call it A or G? Does it matter? It doesn't matter. Okay, I really typically just write it in as A. My acceleration is still negative 9.8. If you like it as G, by all means, call it G, right, for gravity. But that number is not going to be given to us in the problem. We have to remember that. Okay, take a look at your equation sheet. Any of our equations that we could use? The first one? Okay, well, that doesn't have displacement in it. And that's my goal, is to solve for displacement, right? We are using the ones we just wrote down. But I need to solve for displacement. I need to solve for y final or x final, right? If you're looking at your kinematics, we need to be able to apply those in that y direction also. So what do you think? I would agree. I think the second one also. I don't know anything about my final velocity, do I? Do I know how fast it's going at 1 second? I don't, right? And so that takes out equation 1 or 3. So I'm left with equation 2. So equation 2 says y final equals y initial plus VIT plus 1/2 AT squared, right? I'm not writing the Y variable here or the G. I'm just applying what we know in the vertical direction. Is that comfortable with everybody? Okay, so let's go ahead and put in our numbers. We're solving for Y final, so that just stays. I know my Y initial is 0. I dropped it, which means my initial velocity is 0. And I'm left with 1/2 times negative 9.8 times 1 squared. Okay, so our Y final here comes out to be 4.9. Is it positive or negative? Negative 4.9. So the negative here tells us that we are landing 4.9 meters below where we started. Below where we started, okay? So let's take a look at our little tower over here. 4.9 meters is probably only about here. So after 1 second, that's where we are. Okay, let's move now into 2 seconds. Can I just use the same equation but change my time? Yes, I can. I could just go all the way from the beginning. So y final equals 0 plus 0 plus 1/2 a t squared. Okay. I think we're somewhere around negative 19.6. So that might put us about that far on my tower. And my last one is when we're at 3 seconds. So again, we can use the same equation. And this is in the negative 40 something, 48. Oh, negative 44.1. Okay, so that means we're down here about like that after 3 seconds. Okay, you notice we didn't have to start over at where were we at after 1 second, then add that, right? We can just start from what we know of our original information. Okay, I want you to come look at this picture here, right? If our object started at the top, after 1 second, it's only covered this much. After 2 seconds, it covers a much bigger gap, right? The gap between 0 and 1 is much smaller than the gap between 1 and 2. And then after the next second that goes by, that's an even bigger gap, right? That's the visual of acceleration, right? With every second that goes by, my velocity has increased by 9.8 meters per second. So I'm covering much more distance. So this kind of gives us a good picture of what acceleration really looks like. Okay? Tell me what questions Tell me what questions do we have on that problem? Yeah.
So did 70 meters there have?
Yeah, we didn't even need it, right? We didn't need it. If we did, we would have plugged in, we could have plugged in 70 as our initial displacement. We could have found our final displacement and we would have had to subtract. Yeah. Yeah, it's just kind of an extra. And that would have told us basically how high we are. It wouldn't have told us how far we dropped. It would have been a little bit of a different answer there. I prefer not to mess with that if I don't have to. Right? That's why I like to make my initial displacement 0. Go back. At 2 seconds, our velocity was negative 19.6. Would we expect our velocity to be faster or slower? Faster, right? Because we're throwing it downward. It's not starting with a 0, it's starting with a throw. So, okay, let's see this. It says, suppose the ball from the last problem is thrown downward with an initial velocity of 3 meters per second instead of being dropped. What would its position be after 2 seconds? So if we use the same equation, y final equals y initial plus vit plus 1/2 at squared. Can I use that same equation? Yeah, because the only thing that changed is initial velocity. I still don't know final velocity, so I have to go initial. So now I'm going to say y final is what I'm solving for, 0. But is this one 0 this time? No, it is. What is it? Okay, is it positive 3 or negative 3? A negative 3. See this? It's thrown downward. We have to use context clues here to help with our numbers. So negative 3 is my initial velocity. My time is 2. 1/2 negative 9.8 times 2 squared. Okay, we have to use context clues there to tell me that it's negative. A positive 3 would indicate that we were throwing it in the upward direction. Okay, but we're throwing it downward. Is that about what we had? Negative 25.6 meters? So does that match our expectation of a moving faster? An object moving faster? Right? It went from 19.6 to now 25.6. So at 2 seconds, it is moving faster after being thrown. A person throws a ball upward into the air with an initial velocity of 15 meters per second. Calculate how high it goes and how long the ball is in the air until it reaches his hand again. Okay, so here's our diagram. Okay, there's our little diagram. Let's start picking out what we know from the problem. We know initial velocity is equal to 15. Is it positive 15 or negative 15? It's positive, right? We're throwing it upward into the air. Calculate how high it goes. What's that mean? Final displacement, so YF is my question mark, and time is my question mark. So it doesn't look like I'm given a lot here. But there's two variables that we know. Okay, what's one of those variables that we just know? Initial displacement we think is always 0. And what do we know about the acceleration of my problem since it is vertical? Negative 9.8. Okay, when I'm talking about how high the ball goes, does that mean am I picturing the whole motion here? Or am I just picturing the first half? Just the first half. Now, we need to be really careful about this. There are a lot of parts of our problem where maybe we only focus on the first half, or maybe we only focus on the second half. So we can break our problem into a lot of different parts, right? Really, any segment of our motion we can break into and focus on that part. So if I'm just talking about the first part of my motion, that stops right here, what do I know about my velocity of my object at that point? Right, so my final velocity right up at the top of my motion is 0. Now, is my final velocity 0 right down here? Right, if I was talking about right here, is my final velocity 0? Yeah, but when we talk about final velocity at the end of the motion, we're like talking about, yeah, like the instant before, right? We're not talking about it hits the ground, comes to a stop. If we're looking about final velocity, we're talking about like the instant before it hits the ground. Yeah. So it's 0 up there. Tell me what equation you think we could use to help me solve for final displacement if we know my final velocity is 0. What do we think? Will the first one work to solve for final displacement? No. Will the second one work? No, because I'm missing what? Time. So do I have to use my third one? I need to use my third, okay? So that is VF squared equals VI squared plus 2A delta Y in this case. Final velocity we said is 0. Do I need to square it if it's 0? No. Okay. VI squared is 15 squared plus 2A Y final. And we know delta is final minus initial. So do I need to put in Y final minus 0? I don't, right? So I'm just going to keep that as Y final. Now we just algebraically solve, right? I'm going to have to do what with my 15 squared? I need to square it, then subtract it to the other side. Okay, would we expect our displacement here to be positive or negative? Positive, because I'm throwing it upward into the air. So I squared that, and then I subtracted over. Then I divided by, 2 times 9.8, and I got Y final somewhere around 11.5 meters. Okay, tell me, do you have questions about that one? Okay. The next thing we need to look at is solving for the time it takes until it reaches his hand again. Any thoughts on how we could go about doing that? Can we use the first one? Okay, what do we know about, do we know the final velocity of our object when it reaches his hand again? We don't. We don't. Unfortunately, we don't. And we don't know time.
It's gonna have to be zero. No, we don't have time.
Okay, so let me walk you through a couple options. If I wanted to solve for it without knowing anything about final velocity, I'd have to use the second, wouldn't I? And at his hand again, y final would be equal to 0, right? At his hand again, my final displacement would be 0. So it would look like this. I don't want you to write this down. I just want you to watch, okay? Because this is not how we're going to solve it. I'm going to show you one way, and then I'm going to show you a shortcut. Okay, so let me show you the long way, and then we'll walk through. So knowing what I know right now, I would have to say final displacement is 0, initial displacement is 0, vi times t plus 1/2 a t squared. So we're in a situation now where we have a t squared and a t. Any thoughts on mathematically what would have to happen there? What'd you say? We would have to use the quadratic formula, right? Because we have a t squared and a t. So that's like not a great option. It's an option. We could do it, but it's not my favorite option. There will be some scenarios in which we have to do it, in which the method I show you is not going to work. But for right now, it's going to work for us, okay? I'm going to show you later how we'll use the quadratic, and we'll be able to put it into our calculator, and it'll make it nice and easy. But the way that I think we could do it simpler is this. For problems that are symmetrical, okay, do you know what I mean when I say symmetrical? They're going to go straight up and come straight back down. That is symmetrical motion. Okay, objects that go straight up and straight back down. An object, or an example of one that is non-symmetrical is an object that goes like this, up into the air and then way down, right? That's non-symmetrical motion, isn't it? Would we agree with that? Okay, so our problem right now is symmetrical. And so what we have to know to be true is that the time it takes to go up is going to be equal to the time it takes to come down. Okay, let me say that again. The time it takes to go up is equal to the time it takes to come down. So that means what we can do is solve for time on the way up and then multiply it by 2. Right? So I call that the shortcut method, because if I know it's going to take the same amount of time to go up as it does to come down, I can solve for the time it takes to reach its peak height and then just multiply it by 2. Okay? Yeah, go ahead.
But doesn't it start it going up at 15 meters per second?
Yep. Okay, so it starts, that's a good question. It starts at 15 meters per second, and what does it work to? 0. And then it starts at 0, and it works to negative 15 meters per second. So it will reach the same speed at your hand as it was originally. It will just be an opposite sign. Okay? So the speed that it reaches, and that was when we said, Caitlin, you had a good point about that earlier. We don't know its speed at its hand. Technically we do, we just didn't know it yet. Okay, but an object will reach the same speed at the starting point, just in an opposite direction. That's only true in symmetrical motion. Okay, so let's solve for the time at peak height. And at peak height, we know VF is equal to 0. So we can use our first kinematics equation. VF equals VI plus AT. Okay, but my velocity final is only 0 at peak height. It's not the full motion. So 15 divided by 9.8 gives me 1.53 seconds. That is only on the way up. But I know for my full time, I'm going to multiply that by 2, and I get 3.06 seconds. If I solved my quadratic, I would have had the same answer. Why am I using my old calculator? Yep, this time right here is only representing the time to reach its peak height, because the only time our final velocity is 0 is at its highest point. So this time, 1.53 seconds, the time it takes to reach a velocity of 0 is 1.53. So that's the way up, and then we know the way down is going to take the same amount of time, so that's why we multiply by 2. So I plugged it into my calculator into our quadratic program, and I get the same thing, 3.06. Okay, we're going to